My seatmate this morning pointed out to me that I am the only practicing scientist on the program for this meeting, and so I have been listening with great interest to discussions of business and policy, and needless to say, I bring a somewhat different perspective to these matters. Science is important not only for defining what needs to be done to address the issues of greenhouse gas emissions, but also sets powerful boundaries on what's possible and what isn't possible that are independent of whatever business deals or policy arrangements you make. What I'd like to do this morning is to tell you what one large legacy company, I learned this morning I'm a legacy company, is doing to increase the supply of clean energy in the world. I'll tell you a little bit first about some of the thinking that's gone on behind what we're doing, and then give you two mini case studies in two projects that we're about. I'd like to start off with this chart, which I think you can learn a lot from this chart. It shows where the U.S. has gotten its energy over the last 150 years. And you can see before the Civil War in 1850, most of the U.S. energy came from wood. And as we successively had the Industrial Revolution in the late 19th century with coal, the Mobility Revolution in the early to mid 20th century with oil, gas starting to come in the last 60 years or so, and then a small wedge of nuclear in the last few decades of this chart. And of course, the renewables that is of such great interest to many people in this audience is that tiny pink bar in the last two bits of the chart. Now, we have, if we're interested in reining in greenhouse gas concentrations, we have about 3 bars more on this chart before the concentration will get to 550 ppm or so, at which point many scientists say will be dangerously interfering with the climate system. But the downside of this chart is that they change only on decadal timescales. They change slowly. And for those of us who are interested in making material changes in energy supply to meet the dual challenges of energy security and greenhouse gas emissions, it's interesting to ask why it is that these rates are so much slower than Moore's law, which typifies IT, or even the rates that typify the life sciences, somewhat longer because of clinical trials. And there are really 4 reasons why energy is different, and you really have to understand those if you want to innovate in energy, I think. The first is the issue of scale. Scale is about big stuff. It's about big infrastructure, power plants that cost billions of dollars, refineries that cost billions of dollars. It's about large amounts of material. The U.S. uses 1 billion tons a year of coal. The world uses 2 billion tons a year of oil. And it's, of course, about large numbers of units and growing numbers of units. In the first 20 years of this century, more automobiles will be built than were built in the entire 20th century. That issue of scale means that large capital is required to make a difference. And it means also that you will do well to leverage, to the extent that you can, the existing infrastructure. And for that reason, I think that large energy companies must be part of whatever changes are going to take place in the future if they are to be material. The second issue is the issue of longevity. Large equipment lives for a long time. Power plants last for 50 years. BP cannot unilaterally change the kind of fuel that it produces because it has to work for most of the automobiles that are out there in the market. There's also the issue of ubiquity. Energy is all around us for heat, light, mobility. We hardly think about it. Yet that means that there are many players who have direct interests in energy: consumers, producers, governments, NGOs. Those interests don't always align, and so things move slowly. And finally, there's the issue of incumbency. New energy technologies have to compete with existing technologies. We already have great ways of providing heat, light, and mobility. Anything new that you bring in has got to compete with those and the vested interests associated with them. It's not like, for example, the introduction of cell phones. When cell phones came out, they provided an entirely new capability, and the early adopters were willing to pay very high costs in order to have that, because you couldn't get it any other way. The same is not true for energy, at least from the consumer perspective. So, given all of those issues, how do we go about evaluating technology options? I came newly into the energy business 4 years ago from an academic career, and like all good academics, I said we had better understand this problem before deciding what to do. And so I set out on a 1.5-year study with some internal folks in BP to understand the status of the world's energy, what the trends were, and what technologies were likely to play a role in meeting the challenges posed by those trends. What we understood is that there are various criteria by which you should be evaluating energy technologies. The first is the issue of materiality. As you heard this morning, because of the long lifetime of CO2 in the atmosphere, to address greenhouse gas emissions, we have to make major factor of 2 changes in the way in which we produce energy without emissions. Most people don't understand this. Doing things that are immaterial is doubly bad. It's bad because it makes you think you're doing something when you aren't, and it also distracts resources from doing something material. And the world has finite resources, whether it's financial, brain power, or tolerance for change, to address the issues that energy faces. The second is the issue of current technology status and plausible headroom. This is about the cost curves. It's about what you might imagine technology developing over in the next couple decades. So, for example, wind has been around for 1,000 years, and yet there are marginal improvements you might be able to make. But compared to the potential for biology, for example, not much. Budgets are really important. Economics drives the world. We will couple emissions with economics through carbon pricing, ultimately, in this country, and you've got to pay attention to those. How many dollars per ton of CO2 do you save, or how many dollars per gigajoule are you spending? There are other costs, reliability, intermittency. When we get to a significant wind fraction, we're still going to have to pay for backup fossil fuels. People don't talk about those costs much right now, but they will be significant. And then there's the issue of social and political acceptability, not only for nuclear power, but for wind, for biofuels. These are growing issues. When you look at this constraint, these set of constraints, there are a few material technologies that emerge. And I want to now take you through brief discussions of 2 of them that we are pursuing at BP. One of them is the issue of hydrogen power, which is BP's term for carbon capture and storage, of which we've heard quite a bit about already this morning, and then to talk about energy biosciences. Let me turn for carbon capture and storage, and while there have been allusions to these numbers in words, it's much more powerful to see them as a figure. This is where the world gets its electricity. 40% from coal, 20% from gas, 6-7% from oil, 15% each from nuclear and hydro, and the other, which was mentioned yesterday at lunchtime, is that very small fraction over there. Most of the world gets its electricity from coal as the major source. Carbon capture and storage, and here illustrated by a project that we're hoping to do in California, is a way of burning fossil fuels so that you produce hydrogen, use that hydrogen to make electricity with no CO2 emissions, and take the CO2 produced and stuff it under the ground, where you hope that it will stay for roughly 1,000 years or so.